Good afternoon, everyone. My name is Saknarin. Today, I would like to present my work in the topic is generalized and optimal sequence of width on a progressive iterative approximation method with memory for the square fitting. This is outline for today. We start with my motivation. From this figure, you can see lots of blue points where it is a shape look like one of music notation. Generally, if we need to create a curve of this music notation, the first method that we think about is interpolation. However, this method takes a long time. To improve the speed of this method and also make the fitting results hold the same shape, researchers consider the way of reduce the number of points per curve fitting. In this figure, there is a blue point set of 189 points, and we can call data points. Anyway, we choose only 28 green points per curve fitting instead, and we call green point to control points. And we will got the red curve to be the integer fitting. And after that, if we do some process with the green point again and again, we will got the red curve like this. And the red curve will be better fitting efficiently than the integer fitting. And from this motivation about some process with the green point, it will be the main point or main work of me today with that I will talk later. The next section is about the mathematical formulation. In mathematical model, we set up the formulation of fitting curves problems as for the finite domain of functions such that small f map from Rn0 to Rm0, we need to approximate small f to the big F, such that this term is very small. By shifting and rescaling without loss of generality, consider only small f map from cross interval 0 to 1 N0 to Rm0, and the big F map from cross interval 0 to 1 N0 to Rm0. We assume that Q be a point set to be fit, and parameter T is increasing sequence parameter in the cross interval 0 to 1. At the beginning of the iteration, we select the control point P from Q and generate the piece of bending curve C0 from the equation 1, where Bi is normalized totally positive matrix or NTP of real function. And the collocation matrix of NTP bending basis is in the equation 2, where summation Bi equal to 1. And then we will talk about the progressive iterative approximation, least square progressive iterative approximation, and memory for least square progressive iterative approximation. From three methods can approximate the target curve by the following curve in the equation 3, and from the equation 3 we have P or control point Pik, that the process that we do something about the Pik in the equation 4, we will compute the new control point Pik plus 1 from the equation 4. That's the main thing that is about the pink term delta Ik. From the PIA method or progressive iterative approximation method, delta Ik compute from the first line, and for the second line, it is delta Ik of the LSPAA method. And for MLSPAA method, can compute new control point from delta Ik from this equation. And why we call memory for the square fitting? Because we use delta Ik minus 1 from the previous curve. And moreover, Huang and Wang used omega, gamma, and nu, which is constant width in this equation to compute delta Ik. If we focus on this point and relax constant weight to sequence of width omega k, gamma k, nu k, which is up to the k iteration, and finding the optimal sequence of width, I think this method will got the convergence rate better than the MLSPAA method, and this is the main point and main work that we do in this work. And next will be the main result. For the main result, we generalize to the multidimensional and relaxed optimal sequence, and finding optimal sequence of width on the progressive and iterative approximation method with memory for least square fitting, or we can call GOLSPAA. for the giving data point set Q I in the big I, where the big I is subset of this term, and any initial control point set P I prime in the big I prime, where big I prime is subset of big I, and big I prime is a subset of this term, such that Rj prime less than equal Rj, and let the increasing sequence Tj1 less than Tj2 less than Tjrj in the cross interval 0 to 1, and phi jit is the NTP basis of the vector space of real functions. We start with GLSPIA method, or generalized to multidimensional approximate the data fitting in the equation 6, and we can compute new control point Pi prime k plus 1 from the equation 7, and for the delta I prime k we can compute from the equation 8 with we relax constant weight to the sequence of weight omega k, gamma k, and nu k like this. Moreover, we use delta I prime k minus 1 from the previous curve also, and we use sine I prime t prime equal to the tensor product of the phi j I j prime like this. And then we got the lemma 3.1. Let P be an initial control point set, and let phi be an point set. The control point Pi prime k construct by equation 7 and 8, they can be rewritten as the equation 9, where the phi t prime k plus 1 equal to the equation 10. Then we got the theorem 3.2. We let Bj equal to this matrix and assume that every Bj is positive definite with maximum eigenvalue phi j and minimum eigenvalue phi j prime. Then the series of the data fitting in the multidimensional by the GLSPIA method defined by the equation 6, 7, and 8 with the sequence of weight omega k, gamma k, nu k converge to the least square fitting of the given data point set. For every initial control point set P and any point set phi t prime 0 in the condition in the equation 11. And then we got the theorem 3.3. Under the same assumption of the theorem 3.2, we have the convergence rate of the GLSPIA method at the weight omega k equal to gamma k omega k star, gamma k equal to gamma k star, and nu k equal to nu k star by the spectral radiance of h hat less than 1. Here omega k star, gamma k star, and nu k star are defined by the equation 12. And for simple to choose the sequence of weights to use in our algorithm, we got the corollary 3.4 to reduce the form to simpler to use in the equation 13. And moreover, when we relax or constant weight to the sequence of weights, if we need to finding the optimal sequence of weights, we use the corollary 3.5. Let sk equal to sets of omega k star, gamma k star, nu k star satisfy content in the equation 6. Assume that ck is subset of sk such that ck is non-empty closed convex set. Then the optimal parameter omega k, gamma k, nu k equal to argument mean of this term in equation 14. And then we got the algorithm GOSPAA with input the data like this and parameter sequence of weight omega k, gamma k, nu k, and output is curve ck. Define the increasing sequence tj1 less than tj2 less than 2 tjrj in the cross interval 0 to 1, and compute NTP basis psi I prime equal to tensor product of phi j I j prime, and compute E0 or error from this equation. And after that we compute ck equal this term. And for the GLSPAA or generalized, we use omega k, gamma k, nu k satisfy the theorem 3.2 and corollary 3.4. And for the generalized and optimal sequence of weight or GOLSPAA, we use omega k gamma k nu k equal to argument mean of this term satisfy the corollary 3.5, and then we can compute delta I k prime k, and after that we can compute new control point from this equation and compute the error of each iteration from this equation, and the iteration step will stop when the error less than 10 to the power minus of 7. This is an example of the function map from R1 to R2 with 402 data points, which is fitted with 78 control points. For the numerical result in the table 1, we compare the iteration step, CPU time, and difference of the error of three methods: MLSPAA, GOLSPAA from the theorem 3.2, and GOLSPAA from the corollary 3.4. If we focus on the number of iterations, we can see that GOLSPAA from the theorem 3.2 use the number of iteration is very small and smallest if we compare with error. And for the CPU time, GOLSPAA from the theorem 3.2 use the CPU time smallest at the significant level of 0.05, and for the last column we can see that the value is very small. And from the figure 2, it is the comparison of the error of each iteration. We can see that the blue line is the GOLS from the theorem, and the red line is the MLSPAA, and the black line is GOLSPAA from the corollary. From this graph, we can see that GOLSPAA from the theorem have the convergence rate is better than GOLSPAA from the corollary and MLSPAA method. So we can apply in the second example, which this function map from R1 to R2, but the number of lines in this figure or type pattern is have a lot of lines. Then when we apply in this work, we have to do to fitting like handwriting. And for the numerical result in the table 2, we comparison the CPU times and difference of the error and the quality of the image, PSNR, SNR, SSIM, and RE. From this figure, type pattern have 172 lines. For the CPU time, GOLSPAA use the CPU time smaller than MLSPAA, and for this column, the value is very small. And for the quality of the image, we start with PSNR and SNR. If the value of the PSNR and SNR is high, the quality of the image is high also. So from this result, we can see that the value of SNR and PSNR of GOLSPAA is higher than MLSPAA. And for SSIM, the value if the value of SSIM is close to 1, the quality of the image is high. So in this experiment, GOLSPAA have the quality of the image from SSIM is better than MLSPAA. And for RE value, the RE value, if the RE value close to 0, the quality of the image is high. So GOLSPAA have the value close to 0 than the MLSPAA. So we can conclude that the quality of the image from GOLSPAA is greater than MLSPAA. And if we compare the error of each iteration of GOLSPAA in the blue line and MLSPAA in the red line, we can see that the convergence speed of the GOLSPAA from the theorem is better than the convergence rate of MLSPAA. Then there is another example function that map from R3 to R1 which apply in image imprinting problems. If we consider on the left hand side image, that is the original image of the Thai temple, which is very clear image. On the other hand, when we consider on the right hand side of the image, we can see that there are some noise in the image that we call salt and pepper noise image. For salt and pepper noise is generally caused by defect of camera sensor, software failure, or hardware failure in the image capturing or transmission. The typical intensity value of the pepper noise is close to 0, and for salt noise is close to 1. And for the procedure of how to apply our algorithm GOLSPAA to the image imprinting problems, we start with the input image, and after that we detect unknown pixel and recover unknown pixel. This is the original image which have three channel R, G, and B, and after that we detect unknown pixel, use the salt and pepper noise image like this, and after that we use our algorithm to recover image and got the result like this. For the numerical result, we compare the CPU time and the quality of the image of the GOLSPAA method compared with the traditional method AFMF and median filter. Therefore, for the result shown in this slide, we can see that the blue bar is the GOLSPAA have the value of the PSNR, SNR, and SSIM highest. It means that the quality of the image from GOLSPAA is the highest. And for the value of MSE and RE of GOLSPAA is the lowest. It means that the quality of the image of GOLSPAA is the highest. And for the CPU time, GOLSPAA use the CPU time similar to the AFMF, and for median filter use less CPU time than the GOLS and AFMF. And then we can conclude that our developed GOLSPAA method can effectively apply in this work. Thank you for your attention.